If you've ever worked in RF, you've definitely seen this thing, this intricate web of circles and arcs. I know, it looks incredibly complex, but it's honestly one of the most powerful tools ever invented for our field. So let's dive right in and actually demystify the Smith chart. And hey, for those of you following along with the series, welcome to part 10. This whole explainer is based on a really detailed report on radio frequency propagation by the RFI detectives. Today, we're zeroing in on the Smith chart, because really it's a tool every single RF tech and engineer has to know. So here's how we're going to tackle this. First, we'll start with the why, the quest for power. Then we'll dissect what antenna impedance actually is. After that, we'll introduce the chart as our mental map, learn how to actually plot a point on it, and finally, figure out how to chart a course to a perfect match. Okay, so first things first, why does this chart even exist? Well, it all boils down to one single fundamental goal: getting as much power as we possibly can from our transmitter into our antenna and out into the world. And this quote just hits the nail on the head. You only get maximum power transfer when the impedance of the source, your radio, matches the impedance of the load, your antenna. If they don't match, you're literally just throwing energy away. And this slide shows you exactly what happens. On the left, with a mismatch, that energy has nowhere to go, so it reflects back down the line. This creates what we call standing waves, and you get a high VSWR, or voltage standing wave ratio. Think of VSW as a report card for your system's efficiency. A high VSW is a bad grade. And not only are you losing power, but that reflected energy can actually come back and cook the final amplifier in your transmitter. On the right, though, when everything's matched, all the power gets delivered, you get that beautiful ideal VSW of 1-to-1. That's our goal. So, to understand how to match something, we first have to understand what we're matching. So let's take a closer look at the anatomy of an antenna's impedance. Okay, so at its terminals, an antenna presents what's called a complex impedance. Don't let the name scare you. All it means is that it's made of two parts. There's a real part, R, which is resistance, and then there's an imaginary part, JX, which we call reactance. And we have to deal with both. Now, what's really fascinating here is that even the resistance part is split into two. You've got radiation resistance, that's the good stuff, the part that actually turns our signal into radio waves. But then there's loss resistance. That's just pure waste, energy that gets turned into heat. And then, of course, there's that reactance, which is all about energy that's just kind of stored right around the antenna. Let's try to picture that reactance. Think of it like an invisible bubble of energy right there in the antenna's near field. This energy isn't radiating away. It's just sloshing back and forth between the electric and magnetic fields. Our job, when we're matching an antenna, is to cancel out this reactive energy so that only the useful, real part is left. Okay, so we've got this complex impedance made of different kinds of resistance and this weird reactance. How in the world do we visualize it all and, fix it? Well, this is where our star player comes in. Instead of getting totally lost in complex algebra, we use this, the Smith chart. And honestly, the best way to think about it is as a mental map. It lets us see the impedance, understand the problem, and plot a course to the solution, all visually. It's a game changer. So how is this map constructed? It's really just two sets of lines. You have these full circles, which are lines of constant resistance, and then you have these arcs that curve away from the sides. Those are lines of constant reactance. And the geography is simple. Anything in the top half of the map is inductive, and anything in the bottom half is capacitive. Now, here's the most important part of the whole thing. If this is a map, there has to be a destination, right? A treasure spot. And that spot is right in the smack dab middle of the chart. That center point is a perfect match to our system, usually 50 ohms. It's pure resistance with zero reactance. That is the bullseye we are always aiming for. All right, we understand the layout of our map. Now let's get practical. How do we take a measurement from our antenna and actually put it on the chart? It really boils down to just a few basic steps. First, you normalize, then you plot, then you can account for the transmission line, and then you read your result. Let's just focus on getting the first two right for now. So, step one, normalize. It sounds fancy, but it's super simple. All you do is divide your measured impedance by the system's impedance. So in a typical 50 ohm system, if your antenna measures 25 plus J 50 ohms, you just divide that by 50, and that gives you 0.5 plus J 1.0. That's the number we actually plot on the chart. Now, once you plot that normalized point, its distance from the center defines a brand new circle, a circle of constant SWR. Any point on this circle has the exact same SWR value. And what's really cool is that physically moving down your feed line is represented on the chart by just rotating your point around this circle. It's pretty brilliant. So, we've plotted our starting point. We know where we are on the map. Now for the big question. How do we get to the center? We can't just add more cable. That just moves us around in a circle. We have to add some components to actually change the impedance itself. And that's the whole game of impedance matching, right there. It's about strategically adding components, like inductors and capacitors, to create a path on the chart that moves our point from wherever it is right to that 1.0 bullseye in the middle. And this image shows that journey perfectly. You can literally see the path. You start with your mismatched point. Then you add a series inductor, which moves the point along a constant resistance circle. Then you add a shunt capacitor, which moves it along a different kind of curve, landing it, bam, right at the perfectly matched center. So how do you know which way to go? Well, this cheat sheet is basically your guide. When we add components in series, we move along those resistance circles we already know. But for components in parallel or shunt, it's actually easier to think in terms of admittance, which is just the inverse of impedance. On the chart, this just means we follow a different set of circles. The rules are predictable. It's a graphical system that lets us navigate from literally anywhere on the chart, right to the center. So, to wrap it all up, what are the big takeaways? First, impedance matching is absolutely critical for getting all your power out. Second, the Smith chart isn't scary. It's just a visual map for complex impedance. Third, the center of that map is always your target, a perfect match. And finally, you get there by adding components that move your impedance along predictable paths on that map. You know, when you really think about it, the Smith chart is genius. It takes really complex, headache-inducing math and turns it into an intuitive visual journey. And it just makes you wonder, what other really tough problems in engineering or even other fields could we make simpler if we could just find the right mental map for them?